Hello, everyone, and welcome to the next episode of our application first-hand series. My name is Konstantin Brenkens. I will be your host today, and today's topic is geological samples. So we will have a look at how FLUXANA's laboratory is handling geological samples. And we'll talk about an examples from the beginning of the samples itself, over the analytics preparation and so on, to the report. And yeah, let's get started right away. First of all, the question is, let me get this one. There we go. So the question is, what do we categorize as geological samples? And I want to do a bit of history here. Geological samples is quite a wide spectrum of different materials. And historically, they have always been interesting, mostly to find mineral resources. But due to the changing of industries, the materials that were looked for, that were searched, the minerals that were looked for, changed quite drastically. And this is also reflected in the methods that are used for analyzing these samples nowadays. I just want to give you a recommendation. There is the IHG, the group that you can find in this link here. And they organize, amongst a lot of other things, they organize regular round-robin interlaboratory tests. And we will be talking about a sample that they sent recently at the beginning of the year. We participated in one of these round-robins, and we'll use that as an example to give you an idea about the samples themselves, and also the way to on how to analyze them effectively. And I would also recommend check out their website. There is a lot of interesting reads about the geological samples in general and the activities that they are doing. So definitely check out their website. And yeah, we'll go into the details how FLUXANA analyzes these samples. First of all, what kinds of samples do we have? Let's have a look at what kind of materials we can expect to receive. So one field of samples here is what is usually referred to as prospecting. So that's your classical looking for minerals in general. So people will take soil samples basically, and they will send them to a laboratory for analysis. And we are looking at your traditional minerals here for copper, iron, gold, for example. But over the recent years, modern industry is looking for a lot of different materials. We have some examples later on, but nowadays there is a lot of demand for the analysis of more elements and analytes. And today we are looking a lot of, for example, rare earths and lithium for battery and so on. We'll talk about that in a bit, but yeah, it just shows how the sample itself has changed, and the interesting analytes have changed over the years that these analyzers are working, are used. Another field for a geological sample is soil contamination, and in general soil samples. The field here is different than looking for mineral wealth. We are looking for contaminations here that may have occurred over the past. A very interesting field here is industrial wastelands. So areas where industry was settled and that have long been abandoned. It is often a question, what have remained, what kind of what kind of influence or, well, contaminations have remained after the industries moved on. So again, we are doing geological sample analysis here to find contaminations in the ground here. And usually what is looked for here is more toxic stuff like arsen, cadmium, lead, for example, and also, yeah, the quantity of it. Another field of analysis is sediment analysis, for example, in rivers or other bodies of water. So, and well, again, the field is quite wide, and yeah, what we are using here as a technique is often these drilling cores. You basically drill a hole into the ground, and you take these cores, and you can analyze the composition of them to find, yeah, pollutant, but also the composition. Speaking about composition, another field or another different kind of sample is fracking, or the extraction of natural gas resources. There's quite a lot of interesting literature available about this topic if you just want to Google it and look for documentations. But what it comes down to is that natural gas is usually found in a certain layer or composition, and they are mostly sediments are mostly referred to as mud rocks, and they are considered to be the host rocks for large reservoirs of natural gas. So obviously you want to do your fracking extraction at that point. And so these mud rocks are studied quite intensively to find out the correlation between basically the gas amount and the composition of the mud rocks. The mud rocks themselves are a mix of various minerals like SiO2, calcium carbonate here, and of course also water and other liquids in there. So this is quite an intensive field of analysis, because people want to find out where it is, viable to make these kind of extractions, and they try to find the correlation between the composition of the mud rocks and the content of natural gas, for example. So again here, quite interesting samples that are analyzed. Speaking of the change of analytes, I mentioned before that recently the application that we at FLUXANA are using, they have been improved or built upon with a lot of new and interesting analytes, and rare earth have become very interesting for the industry recently. And analytically, they fall under the same category. We use them in this method of geological samples. And just to give you an idea where they find an application, we have a few examples here. For example, yttrium as an analyte. Forgive the German in the table, but I simply copied that. You can probably find that online. But yeah, yttrium is quite an interesting lead for LED technology, light emitting diodes. So they are used basically in these modern lightings. Another one, lanthan, for example, is used in accumulators. So electric car industry is very interested in these in that element. And finally, erbium, for example, is used in glass fiber optic cables. So yeah, we're talking about internet and all that. So for a lot of industries, these elements become interesting now. And the question is where to get them, and that's where we come back to the geological samples and looking for resources, but different elements now, where historically you would have looked for copper maybe before. Now you're looking for these rare earths because modern industry wants them as a resource. Sample preparation wise, this is quite interesting in terms of I think I already made clear, hopefully, that the the spectrum of the analytes is quite large here. So in FLUXANA's laboratory, when it comes to these geological samples, we actually have a twofold preparation. So what we do is we use our fused bead sample preparation, but we use that for the main components only. So when a geological sample comes in and people want to have it analyzed, first what we do is we make the fused bead, and we make that for the main components only. Reason being, we can analyze the main components with with very high accuracy, because we'll basically eliminate the matrix, so we get high precision analysis. Fusion, I think we've talked about that in other webinars quite in detail. So basically what we do is we take the sample, we mix it with tetraborate. That fusion mixture goes into a platinum crucible. We do our fusion machines, and the result is these glass beads or fused beads. And yeah, FLUXANA has quite a lot of equipment that you can use to automate that preparation. Like we have these electrical fusion machines, but also the gas ones and all the accessories. So if you're interested, check out the other episodes. There's probably a lot more detail about these sample preparations there. The second step, or the second preparation we are doing with the exact same sample, a different part of it, obviously, is we also make a pressed pellet. And the interesting thing here is that in this analytical method, we use the pressed pellet for trace analysis, which usually doesn't work that well. But in this case, we are really looking for low concentrations, and we are really looking for a very few atoms in our samples. And so we cannot use the fused bead preparation in that circumstance, because the high dilution of the fused bead would make it a lot more difficult to find these low concentration of the traces. So in this case, the preparation of a pressed pellet gives us better opportunity to determine the traces. To give you an idea about the amounts we are using here, standard recipe for a fused bead is like 1 gram of sample and 8 gram of tetraborate, for example. A pressed pellet would be the other way around. We use 4 grams of sample and 1 gram of binder, for example. So again, the principle, it's here. If you're interested in the sample prep, there is other episodes that you can watch which go into more detail. And again, FLUXANA provides nice Vaneox presses, different models depending on how many pressed pellets you want to do. Let's go over to the more to the interesting part now, in terms of what do we need for analysis. I already said we use 2 different techniques and 2 different preparations here. So what about the analysis program, the methods which we will be running these samples on, or these preparations? First of all, let's talk about the main components. And this is a table that comes from one of our specifications. So we have the analytes here and the ranges that we analyze. And we grade these 2 out. The chrome, strontium, and zinc are not really considered main components here, due to it being only very low concentration. So just for presentations, we glued them out. But you can see these are your standard oxides. We have aluminum, calcium, and all the usual ones that you would analyze in a lot of mineralic samples. And the measurement program that we are using is actually nothing special. It is our standard raw material program. The reason being is the standards, the certified reference materials that we use for that application, these are actually all mineralic samples. So as a few examples here, let me just go back. The first one is a dolomite. Then the next one, we have some rock samples. We have some phosphate rock samples. We also have a bauxite, a high alumina sample. We have a limestone in there. We have a clay we have quartz, high silica, and we have iron ore. So the raw material already takes all these CRMs that are available, all these mineralic CRMs, and puts them into one measurement program, which again only works in terms of analysis performance on few speed, because you're eliminating the metrics, you're destroying the mineralogy, and you basically have the few speed in the end. So you can put all of these different materials into one calibration and still get quite a good performance out of it. So this allows you to basically use the raw material program for your geological sample, but only for the first part. This is only for the main components. We'll have an example later to see what main components means in concentration units. What equipment are we using here? This in FLUXANA in our lab, we use a wavelengths dispersive unit. This in ours, both of the spectrometers we use are wavelengths dispersive spectrometers with a rhodium tube. Our standard setting for the channel is 50-50, so we are working on 2.5 kilowatts. And the analytical lines that we choose for these applications are mainly the K alpha, so the strongest one. We can use those because, again, we have a high dilution. And for some elements, like, for example, strontium, we are even using an L alpha, a weaker one for analysis, because it gives us enough count rate even on the diluted sample. So that's your typical application program. But again, it's only half of the analysis and the report. Let's have a look at the trace analysis, and this is basically where this is where it gets most interesting. As I said, these ones have changed a lot over the time. So in terms of our specification, again, this is German just because we don't have that one. We didn't find that document in English. So this table we had before, and for us more interesting now is what analytes are considered trace analysis here. And that's the lower part here. And just to give you an idea here, you can see the list is a lot larger than the main components, and there are a lot of asterisks here because they changed a lot over the time, and this also means that our method changed a lot over the time. And we'll get into a bit of the details here now and just talk about this a bit more. So speaking about the sample coming into our lab, the first thing we did, we made the fused bead, and we made the main component analyzer. So this is the first part. And the second part now is the pressed pellet with the same sample. And to give you an idea here, when we are analyzing those, all the red elements marked in this little periodic table here, these are actually analytes that we are analyzing right now. So you can already see it's basically the entire periodic table minus a few. Just for information, the green ones we can't really measure with XRF here. And the yellow ones would be technically possible, but we do not do them yet. It might actually happen that in the future we will include a few of those into our program. Right now we are doing all the red ones. They even include the main components that we already have, but of course we are more interested in the rather exotic ones here. And the analytical program we are using now is quite interesting. As I said before, for the fused beads, we basically use a version of our standard raw material application. For the trace analysis here, this is not really possible, mostly because the analytes change and there is not a lot of CRMs available. So what happened in our laboratory is that we started with a starting method. It was actually a factory method on our spectrometer, and over the time we added more analytes and more standards. And the idea here, remember, this is all on pressed pellets. is that, yeah, we have this baseline calibration, but depending on what future analytes or what present analytes we want to do, we added a lot of standards. So you can see here, this is from our spectrometers method, actually. Some of you might recognize the names here. These are standards names that were added over the time. And this is only a little clip of the 88 standard that we have added so far. So yeah, this is not your typical, you have a calibration table of standards and you just make your regression calibration. This is more like a continuously developed methods. And why do we do that? What are we looking for? What concentration are we actually expecting to find in this press pellet? To give you an idea, this is from one of our control samples that we do regularly, and you can see the main components up here, sodium, magnesium, and so on. They're in the concentration and the percentage range. But when it comes to the trace analyzers in the press pellet, we can actually find pretty low concentration. So, and in this case, I picked molybdenum as an example that this one is below a threshold, so we didn't find half of the ppm here. But when it comes to zinc, we can actually report 2.8. So the concentration range here is a lot lower than we are usually comfortable than reporting. And this would be basically impossible to report on a few speeds. That's why we go for the press pellet to have, you know, better analysis result, better limits of detection, basically. I mentioned before already, there is, when you look at the CRM market, usually you like basing your calibrations on CRM. There is not much available here, mostly because all of these elements of interest, they change all the time, depending on well, they don't change all the time, but they get more and more. And there is not a lot of CRMs available here. So the usual way to solve this, like we have a lack of calibration standards for our method, and the usual way to solve this would be to make synthetic standards from primary oxide. We mix stuff. But on pressed pellets, this is really difficult. It's not really practical, mainly because the mineralic effects of pressed pellet, the particle effects, they come from the material itself. So if you're using synthetic primary oxides, for example, and you just mix them, it doesn't really reflect the reality of the sample. This approach of synthetic standards works perfectly fine in fused bead, but in pressed pellets, it's hard to do. So we have to stick to the real samples, so the real minerals, the real, you know, samples that were dug up somewhere. And again, we have the standard list from our method here, and this guy's with a more, with a description of the material. And just to give you an idea, this is only part of all the standards that we have implemented into our method. The list goes on and on, but you can see these are a lot of different materials, and they were added over time, depending on the availability, basically. Technical wise, or now equipment wise, how do we analyze this now? This is also quite interesting. In this case, we use an energy dispersive unit. Ours has a tungsten tube, and we run it roughly about 50 kV, 1 mA. As energy dispersive units goes, they usually analyze groups of analytes in groups. So the combination of kV and MI changes. You can see down here, there is a different combinations, but they all add up to 50 kV, to 50 watts, basically. And ours has a polarization target. This is actually quite important here, because, what does polarization target mean? We can see in our schematic here, the X-ray tube first hits a target, and then this one reflects the X-ray on our sample. Why is this so important? Again, could go into a lot of details here on how that works. but the general idea or the important thing is that with the polarization of the X-rays, we basically improve our background to signal ratio drastically. So by basically bending the X-rays, to put it simply, we get more netto intensity. We get rid of the scattering and the background noise of the X-ray measurement, which in turn allows us to count small amounts of atoms with a lot higher, with a lot more precision than we would be able in other setups. And this really makes the measurement of the energy dispersive X-ray with the polarization here just perform better. And just to give you an idea, there is in our method that we are currently using, we have 4 conditions running, and this is the example of one. Why am I talking about all of this? It's a simple reason. In order, I don't want to get people the wrong impression here. Handheld X-ray and handheld energy dispersive spectrometers are quite common in this field, mainly because they are mobile and you can just take them into the actual areas that you are analyzing, and you can take measurements. And what we want to point out here is, or what I want to point out is that those are perfectly fine to find and identify certain materials, but they will only be well, they can't do the high performance analysis of a benchtop machine with polarization, simply because they don't have the polarization. They only have the direct excitation and measurement, and also you hold them basically. So they can certainly detect a lot of elements, but doing a precise quantification of your traces here. And remember, I'm just going to go back. We're talking about like a few ppms in reality. This will be hard for a handheld. Not impossible, but hard. Well, we are here at FLUXANA, like I said, we are using it an energy dispersive unit with polarized excitation, and that gives us pretty nice results on the press palette. So speaking of, let's go over an example here. And we'll actually have a look at one of these GOPT round-robin samples that I was talking about before. But first of all, let's talk about what do we get as kind of raw data. And these are actually the samples that the results that we create with our measurements. The top one here is the main component on fused beats, and you can see that this is überschaubar. Like this is manageable. It's a few elements, and well, they're all in percentage. This huge table down here that I had to shrink down to this size to actually make it fit in here. This is the report from the trace analyzer. So a lot more elements, and also a lot more measurement time, because this was done on the pressed palette with the energy dispersive system, like mentioned before. Report-wise, this is from our report for the GOPT sample that was done at the beginning of the year. So here are the results we submitted generally. Ignore the other stuff. This is just, I took this directly from the report. So they put the Z-score and all the other stuff in here. But for us, we reported those ones all in gram per 100 grams, so basically percent. Again, this was done from powder on fused bead. And then the next one is the trace report. And this one was the stuff from before, graded out now. So you can see the list of trace elements is a lot longer. And in our case, here are the results that we reported. This is all ppm. And it's interesting that there are a few elements that we, these are only a few ppm, but there are also some other ones that go up to like hundreds of them. And also some that we did not detect or find, or well, they were below our limit of detection, so we didn't report them. Now, when you participate in these round robins, in the end, you get this report as well. And the interesting thing is that with these samples, we have something that is a perfectly viable secondary standard. So what we usually do at the end of the report, we take those samples and we put them into our existing trace methods. So this is one way to get more calibration standards for your application, which is always a good thing. So to summarize the whole analysis of geological samples as we do them here by FLUXANA is the application itself is developing all the time. There is always coming, there is more analytes and also new ranges of existing analytes that get interesting. So in order to analyze these as, to the best extent we can, we came up with this two-split method. We do an extra or a double preparation. We do the main components with fused beads before, standard stuff, and then we do the traces in a pressed pellet in the concentrated sample, in the concentrated powder, to give the entire periodic table as a result in the end. And we use both techniques here. We use the wavelengths dispersive and the energy dispersive systems that we have at our disposal here to give a good round, a good comparison of all the elements. All right. I hope that gave you a good idea about the very complex and large field of geological samples. As always, feel free to write some comments. Feel free to write questions in the question and answer section. We'll get back to that by email. And thank you very much for your attention. We'll hope to see you on the next webinar, which is coming in June. Find the details on our homepage. And have a nice day, and I'll see you next time. Goodbye.